Hello, everybody. AB Calculus, Chapter 41, Exponential Growth and Decay, Mr. Canfield. There we go, I said all the words. So, we're going to start out and we're going to go through this as quickly as possible. Oh, is it really? No, it's these 2 pages, right? Yeah, okay. So, here we go. So, exponential growth, you've probably heard that before, population growth, things like that. It's going to revolve around this phrase: the rate of change of some quantity is directly proportional to its current value. Another way we can look at that is with this differential equation, dp dt is equal to kp, where it's like the rate of change of a population over time is equal to some constant times the current population. Basically, it's a dy dx equal to some number times y. We are used to seeing x over here, but this is y. And if you remember from the previous lesson, going through and doing this ended up with like ln's when we solved it, and it wound up with being an exponential in the end, e to the x, with like c e to the x, right? So we get the same idea here. So if you go through and you solve this differential equation where there's some generic constant on the front, you wind up getting population is equal to c, where that was our arbitrary constant that we don't know, e to the kt, k being that constant from earlier. So we could think about this constant almost as being some kind of scalar on the growth rate. And this is our key phrase: the rate of change of some quantity is directly proportional to the current value, the current y value, right? So, I know, putting myself to sleep. All right. When driving, you run over a nail. As the air leaks out of the tire, the rate of change of air pressure in pounds per square inch inside the tire is directly proportional to the current pressure. So, directly proportional. So the change in pressure is related to how much pressure there is. So that's how we know dp dt is equal to k times our current pressure. As time goes on, there's less air in the tire, so air escapes less quickly. That's why it's related to the current amount. Okay. So the tire pressure is 45 psi and decreasing by 0.36 psi per minute at the time the nail is struck. Write and solve the differential equation. Okay, so we know dp dt is equal to kp, right? And we know, they tell us dp dt, so we know 0.36 is equal to the tire pressure of 45 times some constant that we don't know. And so we can solve for this constant. .36 divided by 45, 0.008. Okay, so k in this equation is 0.008. Here's the cool thing. This p is equal to c e to the kt. I am able to say that some generic, not generic, sorry. I know the solution curve is going to look like this now. We're allowed to make this leap. If we know it's an exponential growth or decay problem, we're able to solve for k. And this will always solve the same here. If you want a detailed explanation of this solve, it's in chapter 40, just without the k in there. I think it's in there with a number at some point though, but it's all here. So we now know that p is equal to, we still don't know what c is, but we do know e to the 0.008t. So let's see, do we have any other information? Oh, I guess when T is 0, we know the pressure is 45. So we could find out what C is by saying we know the pressure is 45 when T is equal to 0. Wait, that's e to the 0 then. This is just 1. So this C we could even think about as being our initial value, because that's always, when T is equal to 0, the E stuff is going to cancel and it's just going to be the C. So I didn't want to just assume, and I wanted to do a more generic solve of that. But okay, so this is our pressure equation. At any given time T, now we know what our pressure is. So what will the pressure be 10 minutes after the tire was punctured? Is T in minutes? I'm going to assume T is in minutes. 45 e to the 0.008 times 10. So I'm going to go ahead and say I made a mistake somewhere. Oh, Canfield. It's minor. It's super minor. The tire pressure is decreasing by 0.36. So this is what I did here is I calculated as if the tire pressure was increasing. It's decreasing. So just slap a negative on there. That makes our K negative. It doesn't change the 45. It doesn't change anything except when I go up and do this, I need negative 0.008. Okay, 41.540. So this is where common sense is really helpful. I'm glad I made this mistake. I considered reshooting the video and I was like, you know what, let's leave this in. Because we got to be careful about words like increasing and decreasing and indicating positives and negatives. The car is safe to drive as long as the pressure is 20 psi or greater. How long is the car safe to drive? Okay, so I'll do the algebraic solve of this, and then I'll do the calculator solve of this, just because we could see either. So the pressure needs to be 20 or greater. So let's find out when we hit 20. I want to find out what T is. So I'll divide both sides by 45. So I get 20 over 45 is equal to e to the negative 0.008 t. We'll ln both sides. Excuse me. And 20 over 45, they're both divided by 5, so it's 4 over 9. 4 over 9. So, so we'll say ln of 4 over 9 is equal to negative 0.008 t. And then we'll divide by negative 0.008. And you might be like, wait, we're dividing by a negative. Isn't that going to mess it up? No, this ln is going to be a negative. So it's going to be a negative divided by a negative. And cancel out to be some positive. So ln of 4 over 9 divided by, oops, yeah, no, I was right, negative 0.008. 101 minutes. 101.367. No, sorry, 366 minutes. All right. So let's say we didn't want to do that, and we saw that it was a multiple choice question, and they gave us what if they gave us answers that looked like this? We would need to know how to do this. That's why I did that. But if they give us decimal answers, we could always just go in here, set the left-hand side and then the right-hand side equal to each other. And hit graph. Now that's 20, so I already know the original graph isn't going to show it, but I can do window, Ymax, let's say 30. So there's my one, I don't even see the other one yet, so let's see my X max, let's set my X max to, let's say 20 minutes. Oh wait, I know at 10 minutes I'm at 41, so I should at least go up to 41 in my Y. Let's go up to 50 in Y. Let's see where we're at. Oh, that's going to be a while. Let's go out to 50. I know it's 101, okay? I'm just like, what would I do if I didn't have my answer already? Okay, keep going. So eventually, like, oh, maybe like 110 will do it. Cool, I see it's above and below. Perfect, so now I can do my intersection feature 101.366. Same answer, different way to do it. Just depends on how much calculator access we have. So let's go through and review really quick what we did. So we knew we were allowed to use this idea because it said it was proportional to the current y value. Proportional to the current y value. K is proportional, like it's a constant times the current y value. And I keep saying y because this would be dy dx normally. I want us to be thinking about it like that. It helps, at least it helps me. You don't have to think about it like that. It doesn't help you. It helps me. So then what we did was we found, using this information, we were able to solve for k, noting that since it was decreasing, dp dt should have been negative. And then on top of that, knowing our initial condition, some other condition we were able to solve for c, because there's two different constants in this, and we were able to solve for both of them. Once we had that, we had a powerful formula that we could go and find different things with. So this is calculus, this is pre-calculus. And I'm actually going to stop the video there, and then I'll do another example in the next video if it would help you.